Periodic properties. We have already discussed about periodicity. What is periodicity? Once again, we can recollect it. The meaning for the periodicity. When elements are arranged in a series, the properties that was observed in one element is reappear after a regular interval in some other elements. When elements are arranged in a series, the properties that were observed in one element will reappear after a regular intervals in some other elements is known as periodicity. So the properties of elements which reappear after regular intervals is known as periodic properties. The properties which are reappear after regular intervals in some other elements that was found in the first element is known as periodicity. Now the properties which will have this periodic trend is called as periodic properties. The important periodic properties are atomic radius, ionization potential, electron affinity, electronegativity, valency, metallic nature, and the nature of acidic or basic nature of oxides of elements. So these are the important periodic properties. Now let us discuss these periodic properties one by one. The important periodic properties are atomic radius, ionization potential, electron affinity, electronegativity, valency, metallic nature or electropositive nature, the acidic or basic nature of oxides. Now first discuss about the atomic radius. To measure the radius of an atom is very difficult task. Why? Because the first thing is atoms are not exist in free state. Except inert gases, all elements will exist in the form of molecules. The molecules may be due to the combination of atoms belonging to the same element or due to the combination of atoms belonging to different elements. But we never find a single atom in an isolated state. You cannot find a single atom or a single element in the form of atom in its isolated state. That is the one reason. And the second reason is the size of the atom is too small. It is about 10 to the power minus 8 to 10 to the power minus 12 centimeters range, which is also a minute value to calculate. And other reason is, even if you are able to find an atom in a special conditions, there will be a no sharp boundary for the electron cloud of an atom. Because in an atom, we have a nucleus, positively charged nucleus in its center. And around the nucleus, these electrons are revolving in a high velocities. So we can observe the electron cloud only. We cannot identify the position of electron. Just we can observe the electron cloud. This electron cloud has no sharp boundary. These are the three main reasons for why we are unable to calculate atomic radius of an atom in a direct manner. But in the indirect way, we can calculate, or we can assume, we cannot say it's calculation, we can assume or estimate the radius of an atom. Because calculating a radius of a sphere or a ball is a different task when compared to an atom. If you take a ball has certain fixed boundary. From its center, the distance between the center to its boundary can be considered as its radius. But atom is not like that. Even atoms, we cannot claim that atoms are perfect spheres. Just we assume them as spheres. And there is no sharp boundary for its electron cloud. So only way to estimate the radius of the atom is an indirect way to calculate its radius. Because it is easy for us to identify the position of the nucleus by X-ray diffraction method. We can easily find the position of nucleus. So when two atoms are bonded with a bond, we can estimate the exact distance between the nucleus of those two bonded atoms. And half of that nucleus distance can be considered as its radius. Now the other point here is at what type of bond the atoms are bonded together, because there are so many types of bonds involved in the formation of these compounds. For example, if you take a metal, in a metal crystal, metal atoms are bonded with a metallic bond. In some covalent compounds, two atoms are bonded with a covalent bond, or sometimes they may be bonded with a van der Waals bond. So the distance between the nuclei of two adjacent atoms will depend upon the type of the bond in which the atom is involved. That's why atomic radius is also expressed basing on the type of the bond that was involved. The important ways to express the radius of an atom are, number one, metallic radius, covalent radius, van der Waals radius. Now let us discuss these radius one by one. First one is metallic radius. In metal crystal, metal atoms are closely packed together. Like this. Now in a metal crystal, these are the two adjacent metals. For example, in sodium crystal, sodium atoms are closely packed together like this. They are at the minimum distance with each other. Now this is the internuclear distance between the nuclei of two metal atoms that were bonded with a metallic bond. So this internuclear distance is 3.72 angstroms. 3.72 angstroms. So half of this internuclear distance, that is 3.72 by 2, this is 1.86 angstroms. This is considered as metallic radius of sodium. This is considered as metallic radius of sodium. Metallic radius means half of the internuclear distance between the nuclei of two adjacent atoms present in a metal crystal is said to be metallic radius. What is metallic radius? Half of the this is in nucleus. This is the nuclear distance. So half of the nuclear distance between the adjacent atoms that was present in a metallic crystal is known as metallic radius. In a sodium crystal, the internuclear distance is found to be 3.72 angstroms. So half of its internuclear distance can be considered as its metallic radius. Similarly, in a covalent, in Cl2 molecule, 3 chlorine atoms are bonded with a covalent bond. So there will be a overlapping between electron cloud of 2 atoms. That bond is said to be a covalent bond. Now the internuclear distance between these 2 Cl atoms in Cl2 molecule is found to be 3.6 angstroms. 3.6 angstroms. Now half of the internuclear distance, this is 1.8 angstroms. Sorry, this is 1.98 angstroms. The internuclear distance is 1.98 angstroms, and half of it will be 1.98 by 2. This will be 0.99 angstroms. 0.99 angstroms is considered as covalent radius of this chlorine. Now, van der Waals radius. At high pressures and low temperatures, the molecules, the gaseous molecules, are converted into solid state. When they are converted into solid state, the molecules are at a minimum distance with each other. At that state, they have an attraction between 2 molecules. That attraction is said to be van der Waals attraction. So when 2 molecules are in van der Waals attraction, the half of the internuclear distance between the 2 molecules is said to be 3.6 angstroms, and half of the distance, this is considered as its van der Waals radius. 3.6 by 2, that is equal to 3.6 by 2 is equal to 1.8 angstroms. That means for chlorine we have 2 types of radius. The radius of chlorine can be expressed by 2 ways, basing on the type of the bond that it was involved. When in a Cl2 molecule, 2 chlorine atoms are bonded with a covalent bond. 2 chlorine atoms are bonded with a covalent bond. When they are bonded with a covalent bond, half of the internuclear distance is considered as its covalent radius. When it was in a solid state, two different Cl2 molecules are at a minimum distance with each other and binded with a van der Waals forces of attraction. In such a case, the half of the internuclear distance between the two adjacent chlorine atoms is considered as van der Waals radius. For same chlorine, covalent radius is 0.99 angstroms, whereas van der Waals radius is 1.8 angstroms. So, atomic radius. We cannot measure the atomic radius of an atom directly. We cannot measure the atomic radius of an atom directly. Why? Because atoms are not exist in free state. That is the one condition. And second condition, when they are in the form of molecules, and the second condition is atom is too small and its radius is in the range of 10 to the power minus 8 to 10 to the power minus 12 or 13 angstroms. And the third condition is the electron cloud has no sharp boundary. These are the three main reasons for why we are unable to calculate the radius of an atom. Why we are not able to calculate the radius of an atom directly. The main reasons for unable to calculate the radius of an atom directly, because atoms are not exist in atomic state. They always exist in the form of molecules. Atoms always exist in the form of molecules. They never obtained in the form of atoms. That is the first reason. And second reason is the size of the atom is too small to measure. It is approximately 10 to the power minus 8 to 10 to the power minus 12 angstroms range. That is the second reason. And the third reason is that electron cloud is not having a sharp boundary, and we cannot claim it is as a perfect sphere. Because of these reasons, we are calculating the radius of an atom in indirect manner from its molecules or from its molecular state. In the case of molecules also, there are some problems, because in all the molecular states, atoms are not bonded with same type of bonds. There are so many varieties of bonds are there. For example, in metals, the metals are obtained in the form of metal crystals. In a metal crystal, all metal atoms are bonded together with a metallic bond. Or if you take a compounds in a gaseous state, they are bonded with a covalent bond or an ionic bond. Or if you take gases when they are in solid state, gaseous molecules are at a minimum distance and bonded with the van der Waals forces of attraction. So these are several types of bonds when they are involved. While measuring them in indirect way also, we have a difficulty. That's why we have considered different types of atomic radius basing on the bond in which the atoms are involved. Basing on that, the ways that we express these atomic radius are: one is metallic radius, other one is covalent radius, and third one is van der Waals radius. In metallic radius, what is metallic radius? In a metal crystal, metal atoms are bonded with a metallic bond. In a metal crystal, when two atoms are bonded with a metallic bond, half of the internuclear distance between the nuclei of two atoms in a metal crystal is considered as its metallic radius. What is metallic radius? Half of the internuclear distance between two metal atoms in a metal crystal is considered as metallic radius. For example, if you take sodium metal, in sodium metal, 2 sodium atoms, sir, so many sodium atoms are present here. The distance between the nuclei of 2 adjacent sodium atoms, whatever the adjacent atoms, these 2 are adjacent atoms and these 2 are adjacent. So, half of the internuclear distance between these 2 nuclei or half of the internuclear distance between these 2 nuclei, anything can be considered. So, half of the internuclear distance between the nuclei of 2 sodium atoms in a metal crystal is considered as its metallic crystal. Here in sodium metal, the distance between the 2 nuclei of adjacent atoms is found to be 3.72 angstroms. The position of nucleus we can calculate easily with X-ray diffraction methods. Of course, we are unable to calculate the position of electron, but we can calculate the position of its nucleus. So, it was found that in a sodium metal crystal, the distance between the nuclei of 2 adjacent atoms is found to be 3.72 angstroms. So, half of its distance is 1.86 and half of the internuclear distance is 1.86. So, this is considered as metallic radius of sodium. Now, let us consider about covalent radius. The gaseous molecules are bonded with a covalent bond. When 2 atoms are involved in a covalent bond, that is in homoatomic molecules, whether it is a Cl2 or H2 or a O2 or N2 or C, whatever it may be. When 2 atoms belonging to same element are bonded with a single covalent bond, half of the internuclear distance between the nuclei of 2 bonded atoms is considered as its covalent radius. When 2 atoms belonging to same element are involved in a covalent bond, half of the internuclear distance is considered as its covalent radius. For example, when 2 chlorine atoms are involved in a covalent bond to form a Cl2 molecule, the distance between the 2 nuclei of 2 bonded chlorine atoms is 1.98 angstroms. Now, half of the internuclear distance is 1.98 by 2, that is 0.99 angstroms, is the covalent radius of chlorine. When 2 chlorine are bonded with a covalent bond, the distance between the nuclei of 2 bonded atoms is found to be 1.98 angstroms. So, half of its internuclear distance, that is 0.99, is considered as its covalent radius. When this is converted into a solid at high pressures and low temperatures, then a van der Waals attraction is developed between 2 adjacent molecules, chlorine molecules. Now, these 2 chlorine molecules are in van der Waals attraction. Now, at that time, the distance between the nuclei of these 2 chlorine adjacent atoms is found to be 3.6 angstroms. So, half of the nuclear distance, when 2 molecules are in a covalent, in a van der Waals radius, when 2 molecules are in van der Waals bond of attraction. So, half of the internuclear distance between the nucleus of 2 adjacent atoms, when they are in van der Waals attraction, that half of nuclear distance is considered as its van der Waals radius. So, when 2 Cl2 molecules are in van der Waals attraction, the distance between the nuclei of 2 adjacent atoms is found to be 3.6 angstroms and half of its distance is 1.8 angstroms. So, 1.8 angstroms is considered as the van der Waals radius of chlorine. For a same element, covalent radius is only 40% of its van der Waals radius. Now, another term is also in use to express the radius, that is ionic radius. Ionic ion, what is an ion? A charged atom is said to be an ion. A charged atom is said to be an ion. If it is a positive ion, we call it as a cation. If it is a negative ion, we call it as a anion. So when positive ion is formed, when a neutral atom loses one electron, a positive ion is formed. In the formation of a positive ion, one electron was removed from an atom. So in such a case, in that atom, the nucleus positive charge is more than the charge of an electron. So in such cases, this nucleus will pull the electron clouds towards itself strongly. So electron cloud will move closer to the nucleus. That's why positive ions size is smaller than an atom. And for example, this is an atom. This is the electron cloud. Suppose if this atom loses one electron, when it loses one electron, what happens? One electron was removed. So there is no change in the total positive charge of the nucleus. There will be no change in the total positive charge of the nucleus. So when one electron was removed, the residual electrons will move closer to the nucleus. So this is positive ion. For the same atom, positive ion is very smaller than a neutral atom. Suppose if we add one electron to this, then it forms a negative ion. This negative ion size is larger than its neutral atom. Positive ion is smaller than its neutral atom. Negative ion is larger than its neutral atom. If we remove another electron, then you will have 2 units positive charge. In such case, the electron cloud is further shrunken. That means as positive charge increases, the size of the ion gradually decreases. As negative charge increases, the size of the ion gradually increases. Suppose if you add one more electron to this, now the nuclear charge is same, but you will have more radius. So as you are adding electrons, this is neutral atom. As you are adding electrons, the size of atom is gradually increases. If you remove electrons, the size of the atom will gradually decreases as positive charge increases. Sizes increases as negative charge increases. Sizes decreases as positive charge increases. This we consider as ionic radius. Because if effective nuclear charge, that means the charge of nucleus is more than electron's charge. We call it as a difference in the electric charge and the positive charge is said to be effective nuclear charge. If effective nuclear charge is increasing, atomic size is gradually decreases. If effective nuclear charge is decreasing, atomic size is gradually increases. So a neutral atom is larger than a positive ion but smaller than a negative ion. As positive charge increases, ionic size gradually decreases. As negative charge increases, ionic size gradually increases. So in the isoelectronic species, that is which are having same electronic configuration, negative ions will have larger size, whereas positive ions will have smaller size. As negative charge increases, size is also increases. As positive charge increases, size is decreases. For example, neon is a neutral atom which is having 10 electrons. Sodium is also having 10 electrons. Magnesium is also having 10 electrons. Aluminum is also having 10 electrons. And silicon is also having 10 electrons, Si plus 4. Similarly, F minus is having 10 electrons. O minus 2 is also having 10 electrons. N minus 3 is also having 10 electrons. And C minus 4 is also having 10 electrons. So these series of these ions are said to be isoelectronic species. So C4 is greater than O n minus 3 is greater than O minus 2 is greater than F minus is greater than Ne is less than sodium, is less than magnesium, is less than aluminum, is less than silicon. So the smallest ion is silicon and the largest ion is carbon, and their atomic size, ionic sizes are in that trend. This is said to be ionic radius. Now, periodicity. Periodicity means the change of this atomic size along the period and along the group. How it changes is said to be periodicity. The change of this atomic size along the period and along the group is said to be periodicity. Now let us observe the periodicity of this atomic radius.